Kristen de Graauw. I'm a PhD student at West Virginia University. We're here in the Geology and Geography department, and this is the tree ring lab. So there's all kinds of different projects going on in here, but we're going to talk about the Old Hemlock house today. So last time we went to Old Hemlock house and collected cores. Since then, we've mounted the cores on these wooden core mounts using wood glue. And then we sanded the cores down using progressively finer sandpaper so that we can actually see the cellular structure of the tree rings on here. I don't know if you can zoom in on that or not. But you can see all the different rings in there. So that's what all the cores look like right now. We've got all of them here. This is everybody. And now what we're doing, so this is the next step of the tree ring dating process, is we are looking at the rings from these logs, and we're going to look at the variability of ring width. So trees put on annual rings, and those annual rings can be different sizes based on the environmental conditions that the trees are in. So if it's a good year, there's a lot of moisture, the tree's going to put on a big ring. If it's not such a good year, maybe it's a drought year, the tree's going to put on a smaller ring because it's allocating its resources to staying alive during a drought, and so it's not actually putting those towards more growth. So what we do is we look at these patterns of ring width variability in the trees, and we're able to match them up. We can match them up across all of these cores, but we can also match them up with trees from other sites. So this is all Old Hemlock house, but what we're going to do is try to match these up with trees from Cooper's Rock, with trees from Ohio, with trees from down in southern West Virginia. And we're going to see if they have the same patterns of ring width variability. If they do, we'll be able to date these cores. So these living trees, we know we know how old they are because we know what year it is when we've cored them. We can take them back in time, and then we can match them up with these cores and figure out how old these cores are based on these living trees. So that's the process today. And the way that we do that is we use this machine here. It's not very technical. Basically, we have a microscope, and in that microscope, we have some crosshairs. If you actually look down into the lens, you'll see crosshairs. And what we do is we line those crosshairs up with the tree rings. And then we have this stage, and it's a moving stage. You just move this dial here, and it actually moves the stage one way or another. And so what we do is we line up the ring with the crosshairs, move the stage, which moves the core across our field of view, and whenever we hit the next annual ring, we hit this button, and it measures how long that ring actually was. And so we do that for every single ring on this core. We're taking a measurement of the ring width. And we do that for all of our cores. And then we run it through a statistical program that I don't have open. And that program basically tells us how well the tree rings from one sample match up with tree rings from another sample. Where is that? Let me find that. And this program is pretty basic as well. We've had this for a while, but it's matching up all the patterns of ring widths. It's telling us how well they match up, and it's telling us whether or not they match at all. So it's a little bit technical, but I'll walk you through it there. But that's the process. So we're just measuring ring widths and then comparing them against other trees. We also do it by hand. We do what are called skeleton plots, where we actually draw up the ring widths on graph paper, and we're able to look at patterns of ring width variability visually as well as statistically. And so we usually compare the visual versus the statistical. And we'll usually find that the same answers are there for us, but it's a nice way to check. So that's it. That's what we're doing today.